Electrochemistry. David, the science guy. Science rules. Jared, the science guy. Alex, the science gal.
Electrochem? What is that? Electrochemistry? What is that?
So, what is electrochemistry? Electrochemistry is the study of chemical reactions that creates a flow of electrons with the intention of creating an electrical output. So, normally you have a cathode and an anode, which are two pieces of metal, and they're in a solution to create the flow of electrons between them, so you can power something, and it's used to power light bulbs and stuff like that.
What are redox reactions? Before we can understand what an electrochemical cell is, we must first understand the principles of an oxidation-reduction reaction, or redox reaction. In an oxidation-reduction reaction, electrons are transferred. The oxidation reaction is the losing of electrons, while the reduction of a reaction is the gaining of electrons. This can be memorized using the mnemonic oil rig. Oxidation is losing, and reduction is gaining. These two processes must occur at the same time, because if electrons are transferred, they must go from something to something. Now consider the following reactant. Cu plus 2AgNO3 yields 2Ag plus CuNO3 2. So here, there is a transfer of electrons. However, in this balanced equation, this is not clearly shown. So how do we fix this if we want to see where the electrons are moving? Scientists use the concept of oxidation numbers, which are hypothetical numbers given to an atom that demonstrate what this atom would have if it were composed of ions. There are a set of rules that govern what oxidation states an atom has, but we won't get into those for today. Today I'll just show you where the transfer of electron happens. This has an oxidation state of 0, Ags plus 1, NO3 minus 1, Ag 0, Cu plus 2, and NO3 minus 1. So here, Cu goes from a 0 charge to a plus 2 charge. This is oxidation because Cu is now losing 2 electrons to become a plus 2 charge. Similarly, Ag is now going from a plus 1 charge to a 0 charge. This means that it is losing a single electron. Now we see that the transfer of electrons is accurate because here Cu loses 2 electrons while there are 2 Ag atoms that gain 1 electron. So these 2 electrons are transferred correctly. And this is the concept of oxidation and reduction and oxidation numbers. The oxidation and reduction reactions can be looked at separately. These are called half reactions. With the oxidations reaction, we can write Cu yields Cu plus 2 electrons, because this Cu atom is losing 2 electrons. Similarly, the Ag atom is gaining an electron and becoming Ag. These are the 2 half reactions that govern this single reaction.
What is an electrochemical cell? Well, an electrochemical cell uses an oxidation-reduction reaction to convert chemical energy into electrical energy. So let's see how an electrochemical cell is set up. Today we're going to be making our electrochemical cell. First we're going to start with 2 beakers. Now let's add some solution. Today we're going to use a copper sulfate solution. And a zinc sulfate solution. Next, let's add our electrodes. We're going to add a zinc electrode to the zinc sulfate solution and a copper electrode to the copper sulfate solution. Let's connect both of our electrodes using a wire, an external wire. Now we're going to add a salt bridge to connect both of our beakers. This allows for the charge to be balanced. Let's also add a light bulb. So this setup will allow for the redox reaction to occur. So we have sulfate ions and zinc ions in our solution, as well as sulfate ions and copper 2 ions in our copper solution. Now our zinc is going to act as our anode, and the copper as our cathode. In the redox reaction, the oxidation occurs at the anode, so this releases the electrons, and they will flow in this direction to the cathode, which gains electrons at the copper side. And this flow of electrons starts the electricity and will light up our light bulb. This is our electrochemical cell.
Did you know that? An electrochemical cell is also known as a galvanic cell, named after Luigi Galvani. In 1771, when dissecting frog legs, he observed that the leg's muscles twitched. Later, Alessandro Volta explained this phenomenon, that a current had been produced by touching different metals to the bloodstream. Well, now you know.
Cell potential! So we're going to look at a diagram that we made earlier in the video, and this is our electrochemical cell, and there are 2 types of cells. There's galvanic, which put out electricity, which power the light bulb like this one is here, and you can measure that using a voltmeter. So you would hook up the voltmeter right here. We hook up the voltmeter right here, and you're going to get an output for however much charge is going through this galvanic cell. And so it measures the electron flow between the 2 beakers and the output of the cell. There's one other form of electrochemical cell called an electrolytic cell. Now this requires energy being put into the cell rather than energy being put out of the cell like the galvanic. Now this requires a battery. So you would put the battery where in the galvanic cell you would put the voltmeter. So the battery allows the flow of electrons to go through the cell. Now with the electrolytic cell, the flow of electrons goes the other way. So it's reverse from what we had with the galvanic cell going this way. So the electrical output of a galvanic cell can also be determined mathematically. So you take your electrochemical cell reaction, which is 2Fe3 plus 2I minus yields 2Fe2 plus I2. So you would take the 2 half reactions, which in this case are
Fe3 plus I plus E minus yields 2 Fe plus 2. Now, since, and the other one is 2I minus plus yields I2 plus 2E minus. Now in the first one, since we have one electron transferring, we have to double it. So it's 2 Fe3 plus 2E minus yields 2 Fe plus 2. Now, the cell potential, according to our reference sheet, for the Fe3 plus reaction is... Crap, I have this. 0.77 volts. And for the 2I minus, it is negative 0.53 volts. Now, in order to find the total cell potential for our cell, what we do is we just add up these two sums and we get 0.24 volts. Did you know that? Your standard batteries are galvanic dry cells, typically using graphite and zinc electrodes to power your home electronics. Well, now you know. Voltmeters! So this is a voltmeter. Now it shows you the electrical output of our galvanic cell. Now, so what you're going to do is you're going to turn it on to battery, because a galvanic cell is essentially a battery. Now you're going to attach the positive end to the positive end of the battery and the negative end to the negative end of the battery. And it's going to show you that the cell potential, the electrical output of this galvanic cell is 1.343 volts.
Nifty home experiment!
So an electrochemical cell has two electrodes, and when connected, it starts the flow of electricity. We're going to demonstrate this using a lemon battery lab.
So here we have a lemon. We're going to insert a penny into the lemon, and this constitutes the cathode in our reaction. Next, we're going to add a zinc nail, which will serve as the anode in the reaction. This will allow the flow of ions to go from the anode to the cathode, or the zinc to the copper.
Let's look at the reaction. So first, on the zinc nail side, the zinc solid is being oxidized and turning into zinc 2 ion, and it's releasing electrons to flow.
These two electrons will move to the copper side. Here, 2E minus plus Cu2 plus yields copper solid.
And the lemon is acting as an electrolyte to allow the electrons to flow.
Okay, next we'll put the voltmeter into the system, turn it on, and then see how much energy is flowing, or electricity.
As you can see here, the system generated 282 millivolts of electricity.
Song time!
We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to air. Everybody now! We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to air.
free.